Wages World here. It's December 7th, 2019. Do a video. Hey, we're taking a hit here on our magnetosphere. It's at about 1122 kilometers per second. That translates to about 2.5 million miles per hour. Okay? But our geomagnetic activity isn't really rising on our charts. So we must be fending it off pretty well. But I will say this, guys. I'm going to explain something here real quick. You see the colors? That represents density. And I explained this the other day, but this is a good way to show you guys. Okay? So what happens is we get what they call a piling up effect out in front of the Earth of charged particles. Okay? They don't collide with one another like most people think, and I addressed this the other day. Their magnetic fields interact with each other. So they fight each other, they run, they attract, they do this, they do that, and they pile up out in front. That's what you're seeing here. Okay, you're seeing the piling up. That's why it's red. Okay, so when that becomes about the same color of its surroundings, what that means is that some of those dense particles got moved out of the way. How did they get moved out of the way? Guess what? They get moved out of the way by solar wind and that kind of energy. The solar wind runs into this pile of charged particles, grabs some of them with it, and carries them off. Now, what's the evidence for that? Well, this right here, let me show you. See how the orange shows up out in the front, hits the pile. Look what happens. It grabbed it, and we did our job, the Boshock did, in our magnetic field, deflected it around us. But the evidence is right here. You see where it's orange? That's less dense than what it was a minute ago. That's why. Because it grabbed some of those particles and got them out of the way. Alright? That's a very basic way to explain it. But we also recover really, really fast too. Watch. See, it's turning red already? That's because that stuff's always coming. Always. It's just when we get these harder hits, sometimes that's what we see. Okay, it's not always every time, but that is where the solar wind does pick up some of its particles. Just from that piling up effect out in front of us. That's why sometimes we get really low velocity wind speeds that actually hit us pretty hard because they're still grabbing some of those particles. Again, I would say this. You take a ping pong ball and you throw it at me at 10 miles an hour, I'm probably going to not hurt, right? But you take a softball and you throw it at me at 10 miles per hour, it's going to hurt. Because it's more dense, right? Heavier, whatever you want to say there, whatever analogy we want to use. But that's really kind of the way I think about it. So again, we're at the bottom, guys, when it comes to geomagnetic activity. We're still really, really low. So we need to be paying attention to the cosmic ray stuff. And I'm going to go over some of that here real quick. Okay, I'm going to go over this just real quick, guys, because I've been asked a bunch of questions about this here as of late. I did this a few months back, but this is going to be a little bit shorter of an explanation. But essentially, this is what happens, guys. Okay, the cosmic rays hit our atmosphere. You guys can see that here on my graph or this little graphic I made. Hits our atmosphere, and it turns into a pion. There's a lot of stuff up there going on that causes this to turn into a pion, right? Well, the pion has a very fast decay rate. So when it decays, it splits off into these other two. The neutrino and the muon. The neutrino basically it actually will go all the way through the Earth. Now the muon is what we worry about for our human body. That's actually what can make us sick. That's the radiation part of it anyway. Okay? So when we're talking about this, we're actually talking about muons. That's really the danger here. Unless we want to talk about earthquakes and stuff, but we're not going to go into that. Now, again, that's what happens. So, cosmic rays, atmosphere turns into a pion. That turns into a muon and a neutrino. So if you can just remember that a muon is what makes you sick, I mean, that's kind of a basic explanation there. Okay? So, Cosmic rays, solar minimum is underway. Okay, we've talked about this before, right? So the sun's magnetic field is weak. I've said that a lot. Allowing extra cosmic rays into the solar system. So it has a magnetic field protecting our solar system. And when it's weak, more cosmic rays get through. All right? This college here in California, it actually sends balloons up and they take readings. So the neutron counts from that show that cosmic rays reaching Earth in 2019 are at a near a space age peak. Okay, that's a pretty bold statement. But they have evidence. So they got the readings, they got the observation, they got the data. This right here is a graph showing you sunspots, okay, through the years. Now, when we talk about sunspots, we're talking about Earth view sunspots, okay? And how they do this, guys, is they gauge it by how many days you go without any sunspots at all facing Earth. Okay, that's the measurement they're using here for this. So back in 1960, and I don't know how well their equipment was back then, but they're saying 350 days here about 1955, it looks like, or something like that. They had 350 days out of 365 days had sunspots visible to us. Now you can see the steady decrease. Well, we had a lull there in that next one, but then you can see the steady decrease to where we're at now. Okay, and you know, this does follow that 11-year solar cycle. It's very evident. Now let me show you what I mean by that. Okay, this is telling you the number of days without sunspots. So 2019, we've had 259 days so far without sunspots, which gives us a percentage of 76%. Now, if you look at the other stuff down through here, nothing is 76%. 11 years ago, it was 73. There was 268 days without sunspots. Right now, we're at 259. So if we have 11 more days this year, we will meet that record. If we have more than that, then obviously we break that record, and I think we're going to. Okay? I think we're going to blow that record completely out of the water. We're going to, yeah. But you can see how it raises. Okay, back in 2012, 13, and 2015, we didn't experience not even one day without sunspots. This right here is telling you how active the sun gets. And right now, we're really, really low in activity, which is why these cosmic rays are such a big subject. Okay? These are the effects that it has on the human body. Okay? This is just a few of them. Now, I'll take a screenshot if I go through this too fast on you guys. But I've shown this before, and I don't want to, spend a whole lot of time on it. But this is low-level stuff right here, right? Basically, it says yearly dose for airline crews is at about a 9 MSV. That's the unit that they use to measure with there, guys, MSV. Now, in the moderate range, 100 MSV says that's level at a higher, at that level, you have a higher risk of cancer. That's when they first notice it, if you're experiencing 100 MSV. All right, so 400 MSV, that's like, see here, what's it say? Highest hourly radiation recorded at Fukushima. Okay, 4-hour exposure would cause radiation sickness. And you're talking about puking and all kinds of, just really, really sick. And it gets up to 1,000, which would mean that you have a 5% higher chance of cancer. Then you get into the really bad stuff. At 2,000, you're talking about acute radiation sickness, which means you ain't functioning. You're on the ground balled up, okay? 5,000 MSV would kill half of those exposed within 1 month. So if you stayed, in 1 month, you'd be dead. And again here, fatal within days. if you're experiencing 10,000 MSV. Now, that's high radiation, guys. Don't get me wrong. That's really high. You guys can Google this and get this chart, and you can actually look over here at the human body it's got here, and it tells you, breaks it down into like organs and everything, what it does to organs and different parts of our body. I would encourage you guys to go look at that and watch it because it is pretty informative. Just check out the graph itself. So, what I want to show you here is who's affected by this, right? So this kind of explains it pretty well. On the surface, you're getting the single dose, right? Normal conditions. The higher in elevation you go, the more exposure you get. 2 times if you're in the mountains. Commercial airlines, 40 times. Okay? So if you're in an airplane, you're getting 40 times the normal dose of radiation. Now, I think the planes are using some sort of protective materials also nowadays. I don't know that they did in the past. I'm not really sure exactly what they use for that. I know, believe it or not, water is a very good protection against this radiation. Okay, concrete can be, and other materials also, but obviously none of that stuff's on a plane. But now the International Space Station, guys, they experience 250 times the normal dose of what they should. Now, I know for a fact they have some protection up there on it. Now, why is that the case? Well, the reason why is because they're not being protected as well by our magnetic field because they're up too high. Okay? Then, if you go, it says traveling to the moon and Mars, you're going to get 700 times the normal dose. And again, the further you get away, the more that you're going to get there. But also this one, okay? This kind of puts in perspective what normal stuff that we experience here. Okay? Now, the annual cosmic radiation at sea level is less than 1. Okay? Right there's 1. There's 0.1. We're somewhere in the middle, like half, 0.5, we'll just call it. Now, you go down to U.S. annual average of all sources. Okay, they just took all the sources and they put an average to it. That's what they came up with. It's about 5 or 6, I think. According to this graph, anyway. Now, if you guys get sick and have to have a CT scan on your stomach or your abdomen, you're going to experience almost 10 doses of that. Okay? 10 doses of normal dosing is how you have to think of it. Okay? It'd be like you taking an antibiotic and then tomorrow you got to take 10 of them. Okay? So, that's what that means. Now, the DOE, which is Department of Energy, radiation worker annual limit. Once they hit this limit, they're no longer allowed to go work there. They have to go work somewhere else until the time elapses enough that they can go back to it. And that level is only at, looks like at about 20, about what it looks like there. Okay? And then the next one is 6 months on the ISS. That's what they're going to experience, almost 100 units of that. 100 doses. 180-day transit to Mars is going to give you about 500. And then 500 days on Mars is going to give you about 500 doses. Okay? So, guys, that's pretty crazy stuff. It can make you sick really bad. So that's why I talk about this on this is the cosmic ray stuff. And I hope that helped explain things to you guys a little bit more. But let me show you this moon thing I come across. Okay, guys, this is the red flash from the moon. This is an extremely rare phenomenon. I think it's pretty cool. Now, I know there's a lot of controversy about what the moon actually is and what it does and how it works and where it's at and all that kind of thing. I don't really get into that kind of a conversation. I do think people have the right to their own opinion. So, whatever your research has led you to, I'm cool with it. Now, for me, this is what I think. So, again, I don't judge people in that way. But anyway, I just wanted to put that out there because I know that's a very polarized, forgive the pun, conversation. Most people are either like, no way, and other people are like, yes way and there's no in between. So I choose just not to discuss it. But anyway, this is a red flash. See this? Look at this. It's crazy, isn't it? So what is that, right? Well, it says an emerald ray that sometimes lances out from the sun or moon. That's the green flash. When they are about to sink below the horizon. Now this is a red flash. It says Peter Lawrence of Thornton, England, saw one beneath the setting moon on December 1st. Now this only happens when it has to be at a specific angle. Like it's setting. The sun is doing its light rays from around it. There's a whole lot of things that have to come together for this to actually happen, which is why it's so rare. It says as the crescent moon set, it turned vividly orange in color. Then the lower red edge of the moon appeared to detach from the main body, producing a rare lunar red flash. See that? So what causes it? Let's see here. It says, as the moon set, it dipped into a strong temperature inversion layer. Wow. With warm air above cooler air. You guys get that? So, yeah. That's pretty cool. Light rays bend when they cross the layers. In this case, strong enough that ducting occurs. We're not going to go into that. But it says, usually we see green flashes. But this time it was red. Let's see here. So what we're going to do is we're going to watch this movie here real quick. It's pretty cool. Obviously, he set that into motion. You know what this reminds me of? You know how you kind of look out over a desert and look out over pavement? You guys can kind of see that heat wave looking thing. That's kind of what this looks like. I wonder if it's very similar to that. I'm not sure. But essentially, guys, this is kind of a mirage. And they said that there was actually what makes this really extremely rare. They were seeing green flashes too on the craters. You see them? So the green's more not as rare, but this red thing that's happening here is pretty cool. That is rare. Very rare. So, yeah. They were saying, okay, and then down here, guys, there was a article again on Noctalucent clouds. See if I can't find it here. I think it was up here at the top. Yeah, up here in New Zealand. Now the full story's here at this is spaceweather.com, but this right here is the full story. Planetary wave supercharges Noctalucent clouds. Okay, I showed you guys what Noctalucent clouds were the other day, and again, they were able to see these in New Zealand, which is very rare. Okay, it's further up towards the equator than what they typically see these. Now, it's not to say that they haven't seen them there before, because they have. But why is it doing it now? Well, this is why. It's planetary waves is what it says. So there are enormous ripples of temperature and pressure that form in Earth's atmosphere in response to the Coriolis effect forces. Okay, Coriolis is what makes things spin in opposite directions versus north to southern hemisphere. Like our hurricanes in the northern hemisphere spin one direction and the hurricanes in the southern hemisphere spin the other. Now I've also heard people talk about the toilets flushing that way also. I've heard some other stuff saying, hey, that ain't why the toilet does it, but this and that. Now, again, you know, is that what it is? They're saying it is, but that's why they're saying they're seeing this increase as far as it going out. We're getting this big planetary wave. All right, that temperature difference, like I just said, ripples of temperature and pressure that form in Earth's atmosphere in response to the Coriolis effect. It says in this case, a 5-day planetary wave is boosting Noctalucent clouds. In other words, it's sending that temperature difference is causing more water vapor. And like I explained to you guys the other day, the water vapor surrounds, turns into ice around those particles that are up there around in the southern and northern North Pole. And that's what causes these clouds to look the way that they do. And they don't see them until evening, okay, as the sun's setting. I think you probably see it when it rises too, I would think. I'm not for sure on that. But, and what, if you look at this from a distance, you wouldn't even know what this is. But you look at this, see, there's the Noctalucent cloud. I know it doesn't seem very impressive right there, but it is. I'm telling you. And again, that's what it looks like on the satellites that they show. You can see how it's stretching out further towards the equator. But yeah, guys. Also, I'm going to take you guys over here real quick. All right, guys. I got you over here at planetxnews.org. This is Scott's webpage. You guys should really go check this out. He writes lots of articles and stuff here. But I haven't shown you guys in a while how to get to the links. You guys just scroll down if you're on your phone. If you're on your PC, just go over to the right and down a little bit. And here's all the links, okay, to pretty much anything that you're going to need to do the research that we do. These are the tools we look at, okay. Right now, I want to take you over here to USGS, okay. I'm going to pause for a second. Okay, guys, I'm just going to show you today's earthquakes here real quick. As you can notice, you see that first one's in California. Okay, I seen like a little swarm that happened. Okay, there's some more in California. And as we go down, there's a 3 in California, some in Japan, Tonga. Now here's the big one of the day as far as I can see, a 6.0. Now, let me take you guys over here to this one. I do want to show you, I think it's this one. Okay. Map. Excuse me, guys. Sorry about that. Let me back up. Let's just do this. There they are. Okay. Now, as you can see, there's a small little swarm that happened here today. Now, that's real close to the Cascadian subduction zone, guys. So we really need to keep an eye on that. You can see it's right on the fault lines. But that's why I bring it up. But we did have another 6. And again, that would make sense when we're seeing the phi angle and stuff change a lot. But I just wanted to show you guys the earthquake stuff here real quick. There's not going to be a model update tonight, guys. I just didn't have time to put one together. But anyway, I think I am going to end the video here. I'll try to keep you guys updated on all the other stuff. I just thought that moon thing was real cool. I'll tell you what. Hold on a second. Here's that red flash. Okay, I just wanted to show it to you guys again. I just think that's real cool. The flash you're talking about is down here on the bottom. Okay, see that? Now, I was asking myself, too. You guys see these lines, like, rotating up through? I don't know what's causing that. If it's just part of the optical illusion that's going on there. But, yeah. Ain't that, I mean, that's pretty impressive stuff there. It's kind of cool. But, yeah. So, just pay attention, guys. They do, people that fly and stuff, they do give you guys warnings. They post warnings and stuff about the cosmic rays. So, when our geomagnetic activity is really, really low, okay, you're going to hear me come on here and tell you, hey, pay attention to cosmic rays because it is important, okay? People can get sick from this, and I think it's just going to get worse because our sun's in a minimum, which makes us that way, and more cosmic rays are just simply getting through. I mean, that's really as simple as it gets. I can't break it down any more basic than that, but I'm sorry if I didn't explain things very well tonight. I was trying to do it in a basic level as I could, just so you guys can understand more about the cosmic rays and what's going on here. I try to leave out the vocabulary that we typically wouldn't use in our everyday life. And sometimes it's hard to do when we're talking about stuff like this. I will continue to do that for you guys, though, because I really want everybody to be aware. So, anyway, guys, I am going to end the video there. So, this is Wage's World, where truth is the goal and fear is forbidden. God bless, guys.